Alright, so I wanted to help you out and talk about one of the homework problems. Didn't really have a particular one in mind, but there's actually a really good spot to talk about one of them, showing what I want to do today, so when we get there I'll mention it. Where did we end last class? We ended last class by showing that if a rectangle exists, then we can build a rectangle of any arbitrary size, right? You can give me two side lengths and I can build a rectangle that has that particular size. We're going to move on. Those results about rectangles actually sort of lead into very easy proofs of results about triangles, which is what we really care about. Triangles are the most important objects in geometry. And here's our first theorem. If a rectangle exists, then every right triangle has an angle sum of 180 degrees. This will, of course, be a special case. We're going to prove that every triangle has an angle sum of 180 degrees, but proving it for every triangle, turns out the easiest way to do this is to first start off by proving that right triangles do. So the proof, I don't know if I'm going to call this a sketch, but I am going to omit writing down a lot of details. So let's see. Let's let triangle ABC be a right triangle. All right, so this will be such that this angle, measure of angle ABC, is 90 degrees. So here's A, B, C. So now we have our result, our previous result. If a rectangle exists, then I can build a rectangle of any size that I want, right? So we've assumed a rectangle exists. So what I'm going to do is I'm going to build a rectangle on here. So since a rectangle exists, we can construct A, B, C, D as a rectangle. I don't really like the way I worded that. Maybe I should have said we can construct a rectangle A, B, C, D, but let's do that. We can construct a rectangle A, B, C, D. Reads a little bit better, I think. What does that mean? That means that's also a right angle. The angle D is also a right angle. And I've got two triangles in this picture. I've got two right triangles in this picture. Let's look at their angle sums. So let's let X be the angle sum of triangle ABC. And let's let Y be the angle sum of triangle, the other triangle, ADC. What is the sum of x plus y? take all these angles and add them all together, what do they add up to?
360.
360, right? Because it's just the angle sum of a rectangle. Now, x plus y equals 360 degrees, and this is because ABCD is a rectangle. And that's important. That's a really important observation because we know triangles can have angle sums less than 180, right? That's a Curie-Legendre theorem. But what does that mean? Say x is less than 180. What does that mean about y?
Kind of greater.
Yeah, I mean, if x is less than 180, y would be greater than 180, and that's a contradiction, right? We cannot have triangles with angle sums greater than 180. So if x can't be less than 180, it must be equal to 180, and then so is y. So we started off with an arbitrary right triangle, and we've shown that that arbitrary right triangle has a angle sum 180 that establishes the theorem. So I really want to say now again. Let's think of another word. So finally, if x is less than 180, then y is bigger than 180, contradicting Curie-Legendre. Therefore, x equals 180. Done. Again, the catch is if a rectangle exists, right? If a rectangle doesn't necessarily exist, then we can't prove this. And the proof fundamentally relied on the fact that rectangles exist, because then we were able to build this rectangle here. Any questions? All right, so again, just sort of a special case of what we're going to have now is our next theorem is going to say if a rectangle exists, then every triangle has an angle sum of 180. So I'm being a little bit lazy here because it's already on the board. This will truly be a sketch. I'm not going to even write down any words, I don't think. We'll just sort of talk about this. How would you prove this? Well, take any triangle. Take any triangle and cut it into two right triangles by coming into an appropriate vertex and dropping a perpendicular. Now you might say, hold on, how do I know that this perpendicular actually lies inside the triangle? Right? That's a valid question, right? What if you come into this and you try to drop a perpendicular? Now you're outside the triangle. There's two ways you can handle this. One is this argument will actually work in this case, or the other is that there always has to be some perpendicular on the inside. Namely, it's the two angles in a triangle have to be acute. right? You can't have two angles of angle 90 or bigger. So two have to be acute. You can always do this. You can always choose the appropriate vertex. You have to prove this, but you can always drop a perpendicular inside, or you could not worry about that. You could allow it to fall outside, and the argument will still work. Although you'll have to think about the angle sums in that case. But what's the argument now? Well, now I have two right triangles. And yeah, how about we just give these names? 1, 2, 3, 4. So yeah, let's go through these. The measure of angle 1 plus measure of angle 2 plus measure of angle 3 plus measure of angle 4. Plus both of those, plus 90, plus 90. What would that equal? Well, that's the sum of, the angle sum of two different triangles, right? 194, I know that has to sum to 180. I haven't grouped them together, I probably should have, but that's 180. Plus this other triangle, 2, 90, and 3 is another triangle with 180. Just cancel these now, and you have the result. The angle sum of the original triangle is 180. So really just sort of sketching the proof. You can sort of write down what you want from that. But the crux of it is just drop this perpendicular on the inside of the triangle. Break it into two right triangles and then use our result. Again, the assumption here that I haven't written is that a rectangle exists. Because a rectangle exists, these right triangles have angle sums of 180. Any questions? All right. So there's actually something that I'm doing here that I want to formally prove. We're doing often enough, and I sort of just hand waved it away. I brushed it under the rug the first time, but it's the construction of this perpendicular. Right? Here I have a line. I have a point not on the line, and I'm claiming that this perpendicular exists. Right? How do I know I can do that? And the first time this came up was in a proof where we said, okay, here's a line, here's a point, I'm going to construct a perpendicular, and then I'm going to construct another perpendicular. This one up here is easy. This is just the ray construction postulate that says you have a point on the line, you can construct any angle that you want. But this is very different. I have a point not on the line. How do I know that there's a point down here that when I build the line between them, it gives me a 90-degree angle? And I hand-waved this away the first time. I think I said something about, well, you know you can always construct 90-degree angles, so just build sort of all the 90-degree angles, slide it along if you want, and choose the one that actually passes through this point. But that's not a very rigorous argument. And we're doing this often enough that I really want to make this rigorous, so let's call it a quick, it's a lemma, it's a technical lemma. But we'll state this and prove this formally. I don't think the textbook ever does this, but here's the lemma. Given a line L and a point P not on L, there exists a perpendicular, let's say a line. There exists a line perpendicular to L through P. All right, so that's really formalized that we can do this because we're going to do it all the time. So proof. Here's my line L. Not a straight line at all. Here's my, it's still not straight, but that's okay. Here's line L. Here's my point P. And all I have to do is choose any point. Choose any point Q. Let's call it T. Choose any point T on L. And because I don't want to talk about how to label this point, I need to say I have some point over here. Let's just call this angle 1. And construct or draw angle 1 as shown. Now here's what I can do. Now the ray construction postulate comes in. Ray construction postulate says I can build a ray in this direction with that same angle. Any angle that I want. Okay, so now construct ray T, I'm going to put a point on this, TS. TS, as shown, there's a lot of words going into this that I'm hiding behind the picture. TS, as shown, means that S is sort of on the opposite side of L as P is, right? So, and that's something I can do by the plane separation axiom. S is on the opposite side of P, so as shown, such that angle such that angle 2 is congruent to angle 1. Okay, all I have to do now is use facts about perpendicular bisectors. Let's go far enough down this ray to find a point Q that's the same distance from T as P is. Okay, so finally, choose Q on this ray TS so that TP is equal to TQ. And now the result follows, right? L is a perpendicular bisector of this line segment, PQ. So I have a right angle right there. Because L is the perpendicular bisector of PQ, because P and Q are equidistant from T. the result follows. This is what we're looking for. We were looking for a perpendicular to L passing through P. So, and therefore, I'm just running out of space here, but therefore, PQ is the line we wanted. So this is formally how you would do this. Formally how you would show that you can always construct a perpendicular to a line through any given point, not on the line. I'll never do this again. I will just assume in the future that anytime I need to do this, if I have a point on a line and a line, that a perpendicular exists because we've proven it. But I feel good about no longer having to sort of hand wave about how to do this. This is formally a proof. And again, I don't believe this ever appears in the textbook anywhere. It just sort of seems to brush over it. But does this make sense? Okay, so let's get back to triangles. Oh, yeah, I almost skipped over an important theorem. So we just had if one rectangle exists and every triangle has an angle sum of 180, right? The opposite is also true. So if one triangle exists, having angle sum 180 exists, then a rectangle exists. So this is the converse, right? And this means these are equivalent statements. A rectangle exists if and only if every triangle is angle sum 180. The proof of this I'm not going to go through. It's actually fairly long, fairly complicated. I don't think it's worth our time. So if you want to read it, it's in the text. But we'll leave that one alone. And there's an immediate stronger corollary, which is if one triangle exists that has an angle sum of 180 degrees, then all triangles have angle sum 180 degrees. And this is sort of just the combination, or the culmination of everything we've been doing. It is a combination too, but I'm calling it a corollary because it should follow from the previous results. What happens? If a triangle exists that has an angle, so let's say a 180 degree triangle exists, This is actually fairly hard to prove if you don't have rectangles to work with. I've thought about it a little bit. I've tried to prove this without invoking rectangles, and I wasn't entirely sure how to proceed. But if a 180-degree triangle exists, well, what does this theorem say? It says a rectangle exists, right? So rectangle exists. And we've just spent the entire beginning of this class, excuse me, the entire beginning of this class proving that if a rectangle exists, then all triangles have angle sum 180, right? So all triangles have angle sum 180. So this is at least somewhere where rectangles come in and help us nicely prove some of these results about triangles. Just piecing all of these results together. So even though in neutral geometry, right, in neutral geometry, we can't prove that all triangles have an angle sum of 180. We can only prove that they're 180 or less. What this says is if you build a model for neutral geometry, the moment you build a model, so Euclidean geometry is a model, the moment you build a model, if you have one triangle, if you've got a single triangle in your model where the angle sum is 180, then they all have angle sum 180. And opposite of that is, of course, if a triangle exists with an angle sum less than 180, then they all have angle sum less than 180. So one triangle exists with angle sum less than 180 degrees, then they all do. Why does this follow? Well, I won't write it down. You can write down whatever you want from I guess what I'm about to say, but if that's a really badly written one. If one triangle exists with an angle sum less than 180, well, suppose we have this hypothesis. A triangle exists with an angle sum less than 180, right? Now proceed by contradiction. Suppose this isn't true. Suppose a triangle exists with angle sum equal to 180. What does that mean? Well, from the theorem above, if one exists with an angle sum equal to 180, then they all do, contradicting that this thing even existed in the first place. So you can't sort of have both. If a triangle exists with an angle sum less than 180, then 180-degree triangles can't exist because then they would all have to be 180. So the result immediately follows here. Notice, by the way, I'm not saying that all triangles have the same angle sum. They're just all less than 180. So you can't have triangles with angle sum 1 degree and 179 degrees. But they just all have to be less than 180. And it's sort of an interesting result. It means that this neutral geometry has this all or none property, that either all triangles are the same at 180 or none of them are 180. But with that, we've got, what, 20 minutes, probably enough time to do this proof, and I'll talk about one of these homework problems. And I think in the coming week I'll assign a slightly different theorem, where the hypothesis is slightly different, which says suppose every triangle has the same angle sum. Right, so just suppose they're all the same. Then you can prove that they must also all be 180. Which means that in this case where I'm saying they're all less than 180, that means they also all have to be different, or allowed to be different. But But let's come back to Playfair's postulate. So the Euclidean parallel postulate, or Playfair's, right? Same thing. Is equivalent to the statement that all triangles have angle sum 180. Is equivalent to the statement that the angle sum of every triangle is 180 degrees. So we're adding to our list of equivalent things. Right, remember our list that we've been building. We've got Euclid's fifth postulate. We've shown that's equivalent to the Euclidean parallel postulate, or Playfair's. We showed that that's equivalent to the converse of the alternate interior angle theorem. This is just extending that list. Now we're saying that that's all equivalent to the statement that every triangle has an angle sum of 180 degrees. And we know already that that means that's equivalent to a rectangle existing. So there's quite a long list of equivalent statements here. And the forward direction, this is assigned for homework right now. I believe it's number 11 from 3.5, 3.4. Yeah. So this is 3.4, number 11. And if you're still thinking about this, I'll give you a hint. Just take a triangle. You want to show it has angle sum of 180. All right, so you want to show that if you add up all of those angles, they equal 180. The first step feels like Playfair's, but I'm not actually invoking Playfair's. All I'm doing is saying, come into this point. Maybe I shouldn't call these 1, 2, and 3. How about we just call them angles A, B, and C? Makes you read a little bit better. Come into point C and construct a line that's parallel to the base AB. Not using Playfair's there at all, right? Playfair says there's a unique line through C that's parallel to this one. We're not invoking uniqueness, but we know there exists a line. How? Because I can build a perpendicular and another perpendicular to get that line. And that gives me two other angles. That gives me angle 1 and angle 2 up here. Well, what's true about angle 1 plus angle C plus angle 2? What does that have to add up to? 180, right? Yeah, I really should have put measure. Measure, measure, measure. That's all 180 because they're linear angles. And this is where the Euclidean parallel postulate now comes in. And I'm not going to invoke the Euclidean parallel postulate as it reads. There's an equivalent statement. Equivalent to the Euclidean parallel postulate, if I assume this is true, then I have the converse of the alternate interior angle theorem. Which says what? Converse of alternate interior angle theorem says because these lines are parallel, because they're parallel, and I have this transversal cutting through them, angle 1 and angle A are the same. Angle 2 and angle B are the same. So just replace that with A, replace that with B, and you have the statement. So that is in fact the entire proof. I meant to not exactly do the entire thing, but that really is the entire thing. You just have to write it up nicely now. Okay. So yeah, very, very simple idea. Just construct a parallel through one of the other vertices. Because it's parallel, and because I have the Euclidean parallel postulate, then I can invoke the converse of the alternate interior angle theorem to equate corresponding angles, or not corresponding, but alternate interior angles. Any questions? All right, let's do the backwards direction. More involved. It feels very involved when you read it, but hopefully I can sort of parse out the fact that it's not that bad. So suppose every triangle has angle sum 180. We want to prove that this implies that Playfair's is true. That is, I'm going to take a line, a point not on the line, I want to show there's a unique line through that point parallel to the original. So let L be a line. P, a point not on L. And let M be a parallel line, be a line through P parallel to L that shares a perpendicular transversal T with L. Okay, and we've shown how the T and L exist many times. We've shown before that T and L exist, or T and M. So those are parallel. Here I have T cutting through perpendicularly. Okay, so there's the beginning of our construction. As I promised the first time we did this ever, that we were going to do this a whole bunch of times. So we just start off with L, point not on here. Really what we're doing is we're constructing T, this perpendicular, and then we construct another perpendicular to get M. So what now? Now I want to show that M is the unique parallel line, right? So suppose I have another one. Suppose I have N. So let N be any other line through P. We will show that N must intersect L. And that will establish Playfair's, right? Every other line through P cannot be parallel to L. There's a unique one. It's M. How do we do this? Well, let's proceed by contradiction. So suppose it is. suppose N is parallel to L. And now I'm going to throw a whole bunch of points up on this picture to save having to write down exactly what they are. I'm just going to once again say refer to the picture so you can see what sides everything is on and whatnot. So let's see. Let S be a point on N interior to angle QPR. Haven't told you what Q is, I'm just going to put it on the picture. Here's Q. And where the hell is R? R is up here. I'm not going to write see the figure yet though, because I'm going to throw some more stuff on here. Interior to QPR. So, and let T be a point on L such that measure of angle QTP is less than measure of angle SPR. So, C figure. Because none of this makes any sense without the picture. But let me know when you're caught up writing and I'll explain what these things are. So I've introduced a few points here. What have I introduced? S is a point on N, so S is just a point on N that's interior to this angle, QPR. Q is this point on L where the T intersects it. R is just some point over here on M. In particular, it's on the side where this guy makes an acute angle. Again, lots of writing if I didn't have the picture. And what I'm doing is I'm saying, okay, let T be a point on L. Let T be a point on L so that this angle is less than this angle. How do I know I can do that? Well, in a Euclidean sense, if I'm working in Euclidean geometry, it should be fairly easy to convince yourself of, right? If I want to make this angle very, very, very small, I just have to put T way, way, way out here, right? And this is actually SMSG, the ray construction postulate. It says you choose an angle. I can find, I can choose a point on here so that that angle exists, right? So no matter how small you want to make an angle, I can find T so that I can make this angle as small as I want. But in a Euclidean sense, if you want to make this angle very small, just stretch it out super far and do that so that it's eventually smaller than this guy. Now the only thing I have to argue is that I can do this in such a way that this ray lies on the outside of this triangle. Alright, so let's see. If T is not interior to angle QPS, then ray PS is interior to angle QPT. So PS, the ray PS, intersects QT by the crossbar theorem. Now the crossbar theorem contradicting that n is parallel. Contradicting that n is parallel to L. So therefore, T is on the interior of angle QPS. All right, so what am I saying here? I'm saying that the picture looks like it actually looks like. All I want to have not happen, I don't want PS to sort of do this when I stretch T out far enough. And the reason that can't happen, the reason this ray PT must be on the interior of this angle and PS doesn't sort of go like this, is because if it does go like this, well, crossbar theorem says it has to intersect L. And our assumption is that n is parallel to L. So if we're sticking with our assumption, that can't possibly happen. So this ray PS has to lie outside of this angle here. And it turns out we've built a triangle now with angle sum bigger than 180 degrees. So let's piece some angles together and then we'll be done. So this implies that measure of angle QPT is less than the measure of angle QPS. Do you believe that? Everything looks like it does in this picture, so this angle here should be less than this angle here, because PS lies on the outside of this triangle. Nothing too fancy. And thus, let's piece some angles together. Thus the measure of angle QPT plus the measure of angle QTP well, okay, QPT, this angle right here, QPT, that's less than QPS, so that's less than the measure of angle QPS, plus this angle right here, QTP, we constructed this so that this angle would be less than this angle. Right, remember we chose T in particular to be far enough out that this angle is less than this one. So less than that measure of angle SPR. And we're pretty much out of time, so I'll wrap this up very quickly now. What do these two angles add up to? This angle plus this angle, that's a right angle, right? So this is equal to 90 degrees. Well, that means I've constructed a triangle whose angle sum, this one, less than 90, plus this one, is less than 180. Contradicting that all triangles have angle sum of 180. Right, which implies that the angle sum of triangle QTP is less than 180, which is a contradiction. Which contradicts that all triangles equal 180. Bad language there at the end, but we're out of time, so I'll just write this very quickly. How do we get a contradiction? We assumed n was parallel to L. Therefore, n not parallel to L, and therefore we have Playfair. Playfair's is true. Done. Sorry for going over time. Again, I know it feels very messy, but the idea is very simple. It's just let's construct a triangle with an angle sum less than 180. How do you do it? Well, you choose t far enough out so this angle is very, 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 very small. And that's really the whole construction. We'll stop here, and I'll see you Friday.